Welcome back. Thank you for your interest in this next session. We had a great morning session talking about some of the user program, the goals and aspirations of this conference, as well as the session Create a Digital Twin using IFC. Well, we now have 3 presentations, and these are from our openBIM Awards programs from last year. Just to remind everyone that the current program for 2022 is now open. Information can be found on our website. So if you're inspired by any of these, please feel free to submit. I think the first presentation we have is from Dashuang Li and this project titled the Beijing-Zhangjiakou Railway. Over to you.
Hello everyone. Today I'm honored to present our project, openBIM, implemented on Beijing-Zhangjiakou high-speed railway. First, I will give a brief introduction to this project. The Beijing-Zhangjiakou high-speed railway is not only a critical transportation infrastructure that supports the 2022 Beijing Winter Olympic Games, but also a service railway that promotes the coordinated development of Beijing, Tianjin, and Hebei. This project starts from Beijing North Railway Station in the east, ends at Zhangjiakou South Railway Station in the west. The total length is 174 kilometers. There are 10 stations, which are Beijing North Station, Qinghe Station, Badaling Great Wall Station, Xiahuayuan North Station, and Zhangjiakou Station, and so on. The key projects include the Qinghuayuan Tunnel, the new Badaling Tunnel, the Badaling Great Wall Station, and the Guanting Reservoir Bridge. The participants of this project are organized and managed following the ISO 19650 standard. According to the ISO 19650 standard, the project determined different information requirements as well, including the strategic plan, investment plan, and asset management plan in OIR, business information, technical information, and management information in AIR, project scope, execution work plan, material procurement plan, key engineering and BIM decisions in PIR, as well as technical requirements, business requirements, management requirements in EIR. Finally, the project established the project information model and asset information model for operations. We developed software to realize the whole process of CDE, in which all participants belong to different groups. A complete CDE process for this project is Power Supply Construction Team collects the information and updates the model in Power WIP group. After approval by the team leader, the power supply model and documents can be delivered to shared group. Each team can provide advice on the information in shared group until it is completed. After approval by the stakeholder, the power supply model and documents will be published and uploaded. All information in the process will be saved in the library. Based on the concept of openBIM, the project used more than 20 software, adopted standards such as IFC 2.3, MVDXML, COBE, and so on. The project BIM management team also used ISO 19650 to establish a common data environment, then combined openBIM model with GIS data in China Railway. Based on the COBE standard, data transmission from construction phase to operation phase is realized. We also developed applications of RFID and QR codes. The application of openBIM standards plays a great role in promoting the collaborative advancement of this project. For the strategic alignment, as we all know, the railway projects are extremely complex. One project is divided into multiple sections, and one section contains multiple work sites. Therefore, it is urgent to build a collaborative work ecosystem to accelerate the progress of railway projects and reduce project costs, which coincides with the concept of openBIM. The next part is about the openBIM application. Here's the software ecosystem map. This diagram can be divided into 3 stages: Design, construction, and operation. In the design phase, we adopted the IFC format as the only transmission format for model files. After reviewing via IFC-based model review software, also called MRS, each domain model is integrated into a full scenario openBIM model on SuperMap iDesktop, which provides BIM plus G services for the Railway Engineering Management Platform, also called REMPLAT. In the construction phase, different software is used for analysis and application based on the IFC model. Each application calls the IFC model service provided by REMPLAT and provides API or file return service to REMPLAT according to the IDM or MVD. The generated analysis data or collection results are transmitted back to REMPLAT via XML format files or API. In the handover phase, the construction data in REMPLAT is transmitted to Integrated Maintenance System or IMS via the COBie-based form template and IFC model file. The data delivery from the construction phase to the operation phase is completed to solve the lack of delivery documents and the problems of tracing information during the operation phase that often occurred in previous projects. Next, I will describe in detail the use of openBIM in each stage. First, we will discuss the openBIM in design. In this stage, we used openBIM to create models of bridge, tunnel, track, electric power, traction substation, architectural, HVAC, and steel structure. We developed a plug-in software based on the Bentley platform to realize the definition of railway IFC objects and transform them to IFC. This is the class editor interface. In this software, we can define the railway IFC classes and their inheritance relations, related geometric properties and non-geometric properties. The railway IFC objects can be exported as the IFC XML format files. And we can manage the inheritance relationship of railway IFC objects. The geometric and non-geometric properties of the model can be displayed in the panel. At the same time, we take ProjectWise as a design collaboration platform which provides design models and data for REMPLAT. The civil drone photography data and GIS map data are merged into iDesktop. Then iDesktop formed a visual display of BIM plus GIS, which are uniformly loaded and managed on the REMPLAT. By embedding the IFC as the model review rule, we adopted model automatic review software to review, and the review report can be generated at the same time. Then, the IFC model was integrated with the iDesktop software, which conforms to the design delivery specification. The second is the openBIM in construction. In this project, we used multiple BSI use cases to provide guidance for the construction and used multiple openBIM-based applications to improve construction efficiency. For example, in the cross-section quality management of tunnel construction, laser scanning workflow was applied to build a point cloud model of the tunnel section, which is used for data analysis to assist construction decision-making. In the digital manufacturing and production prefabrication of the project, we adopted the workflow from BSI use case, and based on openBIM, we realized the digital manufacturing of steel structures and steel rebars, the production of prefabricated beams and prefabricated components, and the integrated construction of bridge assembly. For steel structure manufacturing, we applied ANSI manufacturing module to add manufacturing information to the BIM model. The CNC manufacturing program can be generated, and it was directly recognized by the CNC manufacturing equipment to realize the digital manufacturing of the steel structure. For rebar manufacturing, we developed a BIM model-based intelligent data cloud platform, improved the BIM model and data interface of steel manufacturing equipment, combined plan bar, steel intelligent manufacturing management system, and steel digital manufacturing equipment to realize automatic manufacturing based on BIM. For prefabricated bridge, we realized application of factory-based prefabricated bridge, which simplified operations and improved on-site concrete pouring capability. In addition, we have also developed some unique applications with reference to BSI use cases. For example, we performed the finite element analysis with reference to the use case of structural analysis. Based on this application, we can analyze whether the maximum local stress of the lower hanging point meets the lifting requirements. Relying on established BIM model and referring to the BSI use case, we simulated the tunnel excavation process, which is helpful to predict the excavation status, find the problem of the plan, and visually guide the construction. Through real-time monitoring and simulation of the surrounding blasting vibration of the old Beijing-Zhangjiakou Railway, Qinglong Bridge Station, and Badaling Great Wall, the blasting parameters are adjusted to protect the cultural relics along the line. We also achieve VR and AR applications with reference to the use case of visualization. After obtaining the IFC format model from RAMPLAT, the model is lightened and loaded into UE4. Through the relationship definition, lighting adjustment, rendering optimization, and identification information supplement to achieve VR applications. By implanting RFID chips and QR codes in railway equipment, the facilities and equipment identification corresponding to the space and information in the BIM design model is established. Moreover, based on BSI use case of field and material tracking, we can collect and record the whole process data of manufacturing, inspection, testing, construction, and commissioning via RAMPLAT, which provides a reliable source for quality traceability. We also built the digital twin for tunnel and combined on-site construction data to complete the update from design BIM model to construction BIM model. Finally, a digital asset for delivery is formed. We also adopted a variety of industry standards during the construction period. By applying IFC Rail, BSI spec, and the IFD, EBS, and WBS issued by the CRBIM, we achieved dynamic information traceability during the construction phase, effectively ensuring the construction progress, engineering quality, and safety. The third is openBIM in operation and maintenance. By creating a model information exchange template that meets the COBIT standard, we completed the transfer of digital assets from the construction phase to the operation phase. During the operation phase, we can better use models and data collected from the construction phase. The domains covered by information exchange templates include track, subgrade, bridge, tunnel, disaster monitoring, electricity, communications, power supply, and housing construction. There are 423 kinds in total. By using the IFC BIM model as the data carrier, we integrated information from the design stage and construction stage, then delivered them to the operation party in the form of an asset information model. The IMS integrated assets information model to improve the BIM-based operation and maintenance of public works, electricity, and power supply. In this way, we can realize the transmission sharing of data throughout the life cycle and lay the foundation for the life cycle management of the Beijing-Zhangjiakou high-speed railway. After using openBIM, we have achieved many achievements and benefits. The openBIM achievements can be summarized as the following. 1. The application of the ISO 19650 standard and the CDE in the construction phase has achieved good benefits. 2. Realizing custom extensions to railway IFC objects and attributes. 3. Developing tools for automatic verification of design delivery models based on IFC standards. 4. Based on IFC and CTGML standards to realize the integrated application of B model and GIS for long-term linear engineering. 5. MVDXML format is used to information exchange of openBIM model in multi-domains. 6. Establishing operation-oriented information exchange template based on COBE standard. At last, welcome everyone to take the Beijing-Zhangjiakou high-speed railway, and we hope you enjoyed the super high-speed and excellent journey brought by the Beijing-Zhangjiakou high-speed railway. Thank you.
Thanks, Dashuang. That was really interesting and a great presentation. We move now to our second presentation, the Grosspeter Tower Performance Gap Analysis with Simulation from our presenter, Werner Fehlmann. Over to you, Werner.
Good afternoon. My name is Werner Fehlmann, and with me is André van der Westhuizen. We are here to present our model-based performance gap analysis use case. We at SMART Infrastructure strive to ensure security and well-being within your buildings via the fields of fire safety, security and comfort, and by using our building management platform, the SIGO-CC, like in this use case at the Grosspeter Tower in Basel. By collaborating Siemens with Gruner, the engineering firm who planned the technical systems at Grosspeter Tower Basel, we decided to look at how we could find a new life for the model. That was created during the planning phase to simulate this building's performance. The tower was completed in 2017, and we now have about 4 years' worth of operational data collected during this time with our management platform, the SIGO-CC. Through a series of ICE session workshops, we sat together and worked through the use cases by focusing on the objective of enabling the client, the building operator, to not only validate the performance of his building, but also make performance optimizations to reduce CO2 emissions. The simulation models that were used for the planning of Grosspeter Tower here in Basel can also enjoy a second life during operations. A building is split into various areas. The individual areas are managed by a complex interplay of building automation and security systems. A variable work phase and differing usage requirements pose huge challenges for installed technology. The question is, how can you tell at a glance whether a system is functioning as planned? The solution we came up with was to enable the client operator to identify areas where building performance optimization is required by visualizing the gap between the simulated as designed building performance and the real-time building performance, called performance gap analysis. Comparing actual and target values identifies the gap. This shows the system's deviation from optimum energy efficiency operations. In short, the bigger the gap, the greater the potential for optimization. Let's take a closer look at the gap analysis. Two datasets are required actual values and target values. The target values are often set by the client during the planning phase. These are statistical values that will remain set throughout the project. The target values may also be taken from a building performance simulation. This enables the values to be dynamically adjusted. The actual values can be taken from the data points on the building management platform. The gap value is then calculated using the actual and target values. We would hereby like to show you what role openBIM principles and technical aspects played in this solution, which we came up with to reach the client's objective and what we learned on the way.
During the planning stages of this 22-story, 18,000 square meter office building, Gruner already in 2013 started to make the first performance forecasts during the schematic design project phase, without an IFC model, using SketchUp and Energy Plus, which is a building simulation software, as well as FairFlow for geothermal simulations. Building on this, the building and plan simulations were carried out in 2016 using an IFC model created during the later construction document planning phase. In the process, both the heating and cooling capacity required for dimensioning the expected indoor climate were passed on. In 2017, the tower was commissioned and the Desigo management platform was activated to control the room automation, primary system automation, lighting controls, and the fire detection system. Trends were set up in the platform for individual rooms and systems to keep track of the building current performance and to be able to compare it to the historical values. At this stage, this client was, however, not able to compare the current performance to the as-planned or simulated performance. In 2021, Siemens and Gruner came together. Via the aforementioned I-sessions, we decided to look at how we could activate the model and simulations done during the planning stage to make a one-to-one comparison between the real-life situation and the simulated situation via model-based performance gap analysis in the Desigo BIM viewer. We decided to focus on one floor of the Grosspeter tower and use the data from the room temperature sensors in the real building and juxtapose these with the simulated room temperature in the digital twin. To do this, we needed to not only connect the simulated data with the live data, but also to calculate the gap to display the deviances. Furthermore, we wanted to integrate the geometric model from the planning phases into the live digital twin in the Desigo BIM viewer. Building performance is simulated during planning with the help of a BIM model. The target operational values are calculated within the simulation tool. If the simulated building performance meets the client's requirements, then the building is approved for construction. During the planning phase, the building twin is created on the basis of the architectural, HVAC, and building automation models. The twin is used during implementation to construct the building on site. Later on, during operations, the building automation data in the building twin can be linked up so that it can be used live in application apps or visualized in the Desigo BIM viewer.
Looking back, the main added value between 2013 and 2016 planning phases through using of IFC models was also the better and faster data availability regarding simulation boundaries conditions and related simulation results. There was also more transparent communication of decision-making for building use and internal loads, and business saving through optimization and automation of the planning process. This has led to holistic increase in quality and accuracy of the expected building behavior and lower error costs in planning. The IFC space was parameterized with the use of profiles of room uses, using a common data environment and imported into the Aidan simulation environment from the Swedish software company Equa via the IFC import interface. The pre- and post-processing took place in the authoring software Revit from Autodesk. The quality assurance of the input data was first carried out with the help of SimpleBIM 2015 and then with SolidBri 2016. The simulation results were analyzed using Python scripts, model-based data analysis, visualized in Python and Revit model-based data visualization, and expected from Revit as IFC and Trimble Plan Calnova for building services planning. In the common data environment, each data point was connected to its corresponding IFC element, and the asset ID, or AKS ID in German, written into the IFC sensor, was also the unique identifier in all three data sources. The gap is calculated in the Desigo, and we use the IFC space of the corresponding rooms to display the gap values in a color gradient. In this way, the client has a very quick, intuitive, and understandable way to get a live overview of how his building is performing. The solution here was they used the IFC sensor to act as a data carrier between the three data sources: live, simulated, and gap. The objects in a BIM model serve as data points and information carriers. The data from the common data environment is linked up with data from operations using the standardized IFC interface. In this specific example, we have used the Access ID key from planning as an identifier in the IFC model. This creates a link between the real and simulated worlds. We use this identifier for collaborations with the planner and electricians and as a common denominator for handover to facility management. The standardization of system ID keys with the IFC structure is a key part of this process. Information is incorporated about energy calculation, simulation, and visualizations, and for use in visualization evaluations. Window or various other elements can therefore be used to display energy performance in the building envelope. The room elements thus become the medium for identifying all room-related statuses. In this specific example of a room temperature sensor, the sensor serves as an interface between the real building and the digital twin. The temperature sensor is recorded with identifiers for three values: gap analysis, target value, and actual value. This can be ensured via a model view definition from the IFC. The IFC model is therefore not only used as a medium to transfer information, but also to display the information. Time was spent searching for a standard field to populate the asset ID and three fields to communicate the live, simulated, and gap values in the IFC structure. And we feel that the standardization of the asset ID and data fields for building automation should be considered by buildingSMART in order to ensure a smooth automatic data transfer from planning to operations.
What we have shown here is that BIM enables us to take simulations from the planning phase to be used in the operation. On the one hand, the structural target values can be defined by the building owner, or they can come from a simulation model. If the building performance was simulated with the help of a BIM model during the planning phase, then certain target values are defined for operation. These target values from the planning can now be linked during operation with the real values of the physical building, using a BIM model in the digital twin in the ZiGoTzC BIM viewer. Thus, the simulation gets a second life. Feedback from the live system to the simulation tool now leads to the simulation being further improved and enables operational optimizations to be predicted. On the one hand, the building learns from the simulation tool, and on the other hand, the tool learns from the building. The simulated target values from the planning process can be compared with the actual values from the visualized twin during operations. In doing so, the data is visualized as a digital twin in the BIM viewer on the ZiGoTzC building management platform. This enables the simulation model to be used during the operational phase to improve the building performance. Integrating the system tool into the building management platform environment allows live data from linked systems to be fed back into the simulation. This continually improves the simulation and even enables operational improvement to be predicted. The building can be optimized by the simulation, and the simulation can in turn be improved by data from the building. There's a symbiosis between the two systems, within the digital twin in the BIM viewer at the center. In the ZiGoTzC BIM viewer, the building's actual values can be compared and visually contrasted with the simulated target values. This enables a quick and easy performance gap analysis. Not only can the gap analysis highlight in color on a particular floor, the historical data from a room can also be accessed and analyzed via a trend view. Past values provide a great understanding of the building and the simulation. They form the basis for improvement measures in control and show which systems need to be adjusted.
Just like here at Grosspeter Tower in Basel, the usage profile, occupancy levels, and weather will vary throughout the building's life cycle. Any change to these areas requires agile intervention in building management in order to ensure that the building functions in as optimum a way as possible with the goal of reducing CO2 emissions. Using simulations and the digital twin in the Desigo CC BIM viewer, you can now perform visual building performance gap analysis, identify areas for optimizations, and undertake the necessary interventions directly in the BIM viewer. This project was a collaboration between Gruner AG and Siemens Schweiz AG Smart Infrastructure. From the Gruner side, the project was led by Manuel Frey as Department Leader Digital Planning and Yannick Brandstetter as BIM Project Manager. Siemens has been represented by Werner Fehlmann as Head of National Accounts and BIM Consultant, together with our two BIM experts, André van der Westhuizen and Roman Sonder in Switzerland. This was our presentation, Grosspeter Tower Performance Gap Analysis with Simulation. Thank you very much for your attention.
Well, great presentation from Siemens as always. Thank you very much, Werner, and your contributions there. Well, we get to our final presentation for this session, which is titled Making It Easier with openBIM from Dawid Fedko. So over to you, Dawid.
Good morning, everyone. My name is Dawid Fedko, and I'm a BIM team coordinator in Digital Transformation Department in Mostostal Warszawa, which is a construction company in Poland that belongs to the Acciona Group. And together with my colleague Bartosz Rodak, who played a role of BIM engineer on a construction site, we will present you our project, which is Make It Easier with openBIM. It's a very special project for us because we received multiple awards, including the most important one, buildingSMART International Award in the Community Contribution category. Here you can find our full names, and let's jump to the presentation. The agenda for this presentation is as follows. Firstly, we will introduce our project, and then we can go to the information requirements, BIM uses, openBIM outcomes and impact, and finally lessons learned from this project. The investment name is Primary School in Warsaw-Dzielano district. Our goal for this project was to build a modern and environmentally friendly primary school for 750 children. The investment includes a school building, sport hall and garage. The project was done for a public client, the city of Warsaw, being a design and build contract and completed over 2 years ago. Once construction had completed, financial summaries and satisfactory surveys were carried out, taking into account feedback from construction management, engineering staff, subcontractors, and also from designers. The fact that the project was under budget and had a return on our BIM investment confirms that the project was carried out successfully. The project received few awards, including 3 from the Mayor of Warsaw for its execution and eco-friendly solutions. In the coming slide, I will show you how openBIM enables the success of our project's goals and much more. This construction site was unique for our organization because we achieved far-reaching results in terms of BIM usage and implementation. But let's start from the beginning of the project. We started the project with a series of meetings with the construction management and company management to determine the goals of the project. One of the main goals was to involve people from the construction site to use of BIM to support their daily activities. It was crucial to test different software solutions and adapt them to the real project needs. To increase involvement of our workers, we decided to use openBIM solutions because they are simple and easy to learn. We wanted to transfer gained openBIM knowledge horizontally between construction sites in our company. It was not our first BIM project, but it was first fully openBIM project. As we found, openBIM framework decreased significantly cost of implementation of BIM on the project comparing to using only native models. As I mentioned, it was not our first BIM project, so we could ask, why openBIM? We decided to go with openBIM because of prior problems with BIM implementation based on native software approach. Some of them are BIM and digital skills gap, a high cost of BIM implementation including software, hardware, BIM skilled resources and trainings, blocking processes to native software, limited involvement of project participants, and low BIM usage, site crew depending on input from BIM specialists. For this project, BIM was something completely new for our on-site team and also for subcontractors. Also, for the first time in our construction crew appears position of BIM coordinator. When we start talking to our employees about BIM, we realize that we need to use the language of benefits. When the construction site organizes its facilities, they don't really think about the architectural BIM models. BIM implementation, we started not from the decision what kind of software we need, but from understanding what are the real problems on the construction site. So we started with earthworks. We were asked to specify the ordinate for humus removal to have as little removal as possible. However, due to the high level of groundwaters, there was a risk of flooding. So based on geodetical measurements, we created the model and we indicate the level of excavation to be on a safe side. After analyzing the model, we selected the best solution to avoid problems with high level of grounding water. At the very beginning of the project, we reduced the risk of additional expenses and potential delays. With this work done, we get attention of workers and their trust. So we started to analyze the real construction needs, and we had to think how BIM could help them. So we identify these functionalities that could help them in their daily work. Here you can find information about BIM uses on project with limited scope to not scare people with new functionalities. During the project, we extended use of BIM because we were surprised how quickly people used BIM. After determining BIM uses, we began the mobilization phase. We prepared our own trainings, adapting them to the construction processes and our needs. Construction workers don't need to use native files, this being reserved for designers and BIM coordinators. These workers can, however, easily work with ISC files, which contains the most important information and can be viewed by simple browsers. Because there were no BIM requirements from the client, we were able to create our own, maximizing the use of openBIM standards. At this stage, the rules of information exchange between the stakeholders of the project were established. Software and information exchange platforms were tested. Working in the openBIM standard made it possible to easily and quickly switch between different softwares. In order to ensure a smooth exchange of models, the modeling methods and the required information contained in the elements have been defined. IFC helps us to structurize the project data through buildings, stories, spaces, and classifications. We also created sample models for the modeling requirements. So after mobilization phase, we started to use BIM as a daily base activity. Now I will give a floor to my colleague Bartek, who will explain how it was done on a construction site.
Construction workers spend a lot of time on quantity takeoffs, a requirement to order materials or when they have to settle finished work with subcontractors. On this slide you can see a comparison between the traditional method of quantity takeoffs made using 2D drawings versus that based on BIM models. The BCF format was used to report the completion of work done on site. By implementing such solution, we can analyze the usage of materials over the time. We also trained subcontractors to use BIM models, so that we could cooperate with model-based measurements and accept their work. The UCFC on the construction site makes everyday tasks faster and more effective through the use of few simple tools. The BIM models gave us reliable and precise information regarding the quantities of elements. Quantity takeoff based on the models allowed us to save 75% of time needed for this task. It was used for the acceptance of work, and we achieved 0 annexes for contracted works with BIM-based quantity takeoff. The use of programs for coordination, BIMTrack and BIMCollab, allowed us to detect collisions that would normally be detected only on the construction site during the execution phase. Implementing these platforms for communication, collisions and design errors has improved the process of solving them. Design errors were exchanged by BCF files. It allowed us to avoid many clashes that could have generated additional costs, especially crucial in a design-build type contract, by improving communication with the designers. Regardless of whether you have BIM models, that the digitalization of construction site processes is very advantageous. We can categorize this into access to 2D, 3D documentation, issues registration, acceptance of works, health and safety observation, and information requests and tasks. The main advantage of the platform was the ease of implementation and adaptability to the quality and safety processes that we have in Mostostal. For those kinds of activities, we used IFC models to speed up processes and standardize information by taking automatic reading from model, like issue location. Access to the combined 2D and 3D documentation allowed subcontractors to easily change their methods of work. This way of communication turned out to be more effective and created zero paper waste, which was one of our eco-friendly goals. Efficient communication with subcontractors is the key to success, which is why we use the Dalux platform to communicate with them. Subcontractors have greatly appreciated this platform, taking into account the speed and accuracy of info transfer. The platform allows us to check for issues on drawings, since they each have an assigned location. This often helps us when we want to check if a subcontractor fixed an issue. Here you can see the issue status at the end of the project. On the right, you can see the graph showing task performance through time. Tasks in progress are in orange, tasks reported by subcontractors to be done fixed are in yellow, and tasks finished and accepted by the general contractor are in green. We can conclude from the shape of the graph that the communication between different project participants was at a high level. Throughout the commissioning process, 1,826 issues came up, and we managed to resolve 89% of them within 3 weeks, with the application helping us to manage them all. Time savings and faster information exchange allowed us to deliver a higher quality project, with a particular emphasis on the quality of work. 90% of our subcontractors actively use the CDE platform, thanks to which we are able to introduce digital data-based communication throughout the entire supply chain.
Some of the data received through mobile phones was analyzed using other tools, like for example Power BI. And here you can see example of the number of workers on the construction site. And what is impressive, data was given day by day straight from the subcontractors for our acceptance. On this slide you can see the software ecosystem, and as you can easily notice, thanks to the IFC files, we could guarantee a interoperability and data exchange between different softwares. The final users used only IFC files, which were simple for them and more cost-effective. IFC file could be adjusted to various BIM use cases and allow specific tasks to be done. Most project participants only needed basic or medium-level BIM or digital skills, meaning less software specialists and advanced software knowledge was necessary. So, as I mentioned at the beginning, this project was unique for our organization because of its impact. We have proven that the full openBIM approach is feasible. It supported construction workers in daily task planning and communication exchange with the project participants. The application of BIM have been extended beyond the initial plans in the mobilization phase. By providing an appropriate level of support along with trainings and materials, we made it possible to take the first step into BIM for a large group of people. After the construction process, we gave satisfactory surveys to our team, subcontractors and designers. Subcontractors appreciate the solutions that had been implemented, pointing out the transparency of communication or saving times. It turned out that we had shortened the time needed for checking documents from 10 to 20 minutes down to 45 seconds. Thanks to the cooperation of all people on site, we have achieved our environmental goals, like less paper on our construction site, and also health and safety goals, like improved communication on health and safety issues and digital reporting. Additionally, external and internal audits, like TÜV Nord, Health and Safety Department, distinguished that solution used as a good practice that we should scale on other construction sites, and that is something we have already done. openBIM framework developed in this project has proven to work both on small and large projects. From company perspective, the project aimed to developing openBIM framework that would involve all project participants and could be further scaled to all company projects. The project became the foundation of openBIM strategy development in company on all of the construction sites. The project has shown that openBIM implementation brings huge benefits, allowing us to further scale those solutions, using them as a foundation for further projects. Using IFC-based software allows us to reduce the cost of both software and hardware compared to that required for native formats. The software also reduces the need for training or highly skilled BIM technicians, which allow us to scale up openBIM solutions to our next projects. Currently, over 30 projects are being carried out on the basis of solutions developed on this investment. It now serves us as a foundation for developing more advanced uses and implementing new innovative applications such as point clouds, 360 photos, and AR combined with IFC models. We have developed internal training methods which involve working on IFC models along with BCF files. Those training programs were used as a part of European BIMplement project, which aims to improve the skills of engineering staff. The project has a wide range of impacts that we can divide it into 3 types. Impact on the project level was directly related to the participant involvement and project management improvements. Impact on the company level refers to the replicability of our achievements to our new projects. Impact on the industry level is based on knowledge sharing with our technical partners so that we could grow and develop together. In this section, I will present the impact achieved on the industry level. Based on this project, we shared our knowledge with students from technical universities to show them the implementation of BIM methodology from the practical point of view. The results of this project were used as a start point for 3 projects in Polish chapter of buildingSMART, related to assigning BIM properties and classifications in the model. We also shared our experience in Polish and international conferences. Our gained experience we shared with our main investor Acciona during the worldwide conference BIM Forum. During these two conferences, we promoted openBIM solutions, and thanks to practical workshop, during which we involved both blue and white collar workers, we could encourage them to use openBIM standards. During a project, we collaborate with software vendors to provide them feedback based on experience from site. Some of our ideas and requests are already implemented in software. openBIM is based on giving and sharing information, which encourage every project participants to be collaborative, transparent, and to contribute. That creates more friendly atmosphere and remove the information silos. During my presentation, you could hear about time and cost reductions. It's obvious that BIM must increase productivity of each stakeholder involved in the project. However, I have two important messages for you. First of all, please remember that openBIM is not only for big and sophisticated projects. It can be also beneficial on smaller ones. And the second thought is, please don't think only about yourself. Think about your subcontractors. By efficient engaging them at the very beginning of the project. Working together in openBIM, we can achieve much more. At the end of my presentation, I would like to thank all of the stakeholders that have been involved in this project. Special thanks to our construction team on site.
Thank you for your presentations, everyone. It was interesting, and I think great to see the application of openBIM used within that. Werner, I had a quick question for you. How important is it that it opens? This was a question that came up earlier in one of the other sessions. How important is standards when we consider the acceleration of digital technologies? So what we mean by that is there's no going back once you start adopting digital technologies. Digital twins are an example you cited. How important is it that standards are embedded in that process when standards aren't always considered a development for innovation, let's say that way? Yeah.
Good afternoon. Thank you for the question. Yeah, this would help very much, because if all the planners and the subcontractors also have already working with the standards, then we have less to improve when we taken over some prepared models. For example, what we have seen here, all these sensors, what are done from other planners, which we perhaps also now could take in this simulation project, where we have to go to our BIM viewer, and then from the BIM viewer we show it there everything what was missing in the data we had to add. And this yes, helps standardization, and we also work on that in all our disciplines here in Siemens in the building technologies, that this more and more is defined, and we can collaborate with the planners and the subcontractors.
Interesting. And how much are you reliant on software vendors, let's say, native file formats in delivering that, or are you able to customize some of that yourself?
Internally, we do a lot on Revit, and all what is missing, we are able on our disciplines from the building technologies in security, in safety, in on my chair, in building automation, there we can define this product catalogs in the families. And also everything what is then prepared in the engineering before and the construction, we bring it over to the operation phases and the facility management. And also there is an interesting part, we have in our management platform, the SIGO-CC, we have this BIM viewer. And in the beginning of this year, end of January, Siemens has bought the company Ecodomos with the whole software. And so we use in the future the Ecodomos integrated in the SIGO-CC platform. And this helps us also make more functions and use cases, like these use cases of the performance gap analysis, also use cases to support in general the operations in all disciplines, also in fire and security. And there it helps with all planners use the standardization, and also we do more what was before in a proprietary way. We try more and more to put it on IFC and to make this communication over IFC and request this in that direction. And so also now with this possibility of Ecodomos, we get this common data environment which we can use, and not only in the cloud, also on the premise. This is interesting for a lot of customers who would not like to give for the operation in the next 20 years in the cloud. And then these connections between the sensors and our model. This data point connection has to be done by hand. Of course, we can do a macro and do it, but there is also a function implemented, this cross-link service. And with this cross-link service, we can automate these communications. At the end, all what we do here is really to bring these parts of the model which could be used in the operation, that this is be best prepared to discuss with customers what kind of use cases they need, for example, again, from the simulation or also from other topics of our disciplines, that they have an easier life, use less person who manage this, and it is model based. And at the end, there is also like a data warehousing applications, because the whole informations are all sometimes just a link connected to another data bank. And then with the standardization, it helps. And with the softwares, what are able to bring also a life cycle BIM model, where we add with the live data. And so we support on the standardization with the software and with our environment, not just only make a visualization, also we can at the end control on demand. And so you have not only a visualization, you can also jump in the system, change something, and have the visualization again. And yeah, it's really interesting and it's fun. Thank you.
And just one final question, as we're out of time. But are you currently located in the Zug office there, or are you in Germany? I wasn't sure.
I'm in Switzerland, but what?
Zug, your office in Zug?
No, we are in Zurich now, but the headquarters is in Zug. This is correct from Siemens, yeah.
Yeah, you guys are very kindly hosting our international council in June. So we look forward to seeing a smart building in reality when we visit your offices. So with all of our chapter leaders and our board and our SAC, we look forward to seeing some of your facilities.
Yeah, and also our colleagues will be there. Everything is prepared that we can host you in on this chapter conference.
Fantastic. Right. Well, thank you very much. Thanks to all of our presenters and thanks to our audience. We look forward to the next session, which is actually going to be software vendor digital workflows. We'll be hearing from Solibri, Bentley, Bexel, ArchiCAD, or a consultant for ArchiCAD and a consultant for Revit as well. So we'll be learning a bit more about how to maximize your workflows with those tools. So thank you all very much, and we'll see you on the next session. Bye-bye.
Bye-bye.